Okay, so today's lecture is talking about the characteristics of big data and the dimensions of scalability. All right, so this particular lecture basically is trying to explain to everybody what we really mean by big data, what we tend to see in big data, and to some degree, what are some of the limitations of getting big data to grow or getting big data to become even bigger. Okay. So this is a very simple series of things that we want to talk about. The key term that we want to talk about today is the idea of scalability. Okay. And I will jump into that later on when I get around there. Okay. But this particular lecture is essentially a continuation from the previous week's lecture that talks a little bit about what is big data and how do we classify big data. And then after that, we talk a little bit about how do we apply big data in science communication, which probably is more meaningful when it comes to the way that you sort of design your assignment, okay? So just to recap a little bit about what we discussed last week, big data refers to large, complex data sets that require advanced computational techniques for analysis. Okay. Now, the important thing for big data is that it helps us as science communicators enhance our scientific research. It helps us to be more targeted and more specific with our engagement. And it helps us to actually arrive at a logical decision-making process. Okay. And actually, we talked a little bit about how we can actually utilize big data in science communication, notably in the use of data-driven insights for accurate real-time dissemination of scientific knowledge. So that is essentially what we think about when we think about big data. Okay. So the thing that we also talked about last week, I think this is something that we will actually be recapping as like what are the characteristics of big data. Okay. So on the one hand, the first thing we need to talk about is we also talked about this idea of volume, okay, where the size of the data, okay, matters a lot. How much data are you actually working with? How much data are you actually trying to store, or how much data are you trying to process at one point in time? Okay, so the first thing that we need to consider is the degree of the volume, okay, of how much data you're dealing with. The second thing has to do with velocity. So how rapidly does data get produced? Okay. So if you consider, say, a platform such as Twitter, okay, Twitter produces a lot of data all the time. You know, the second anybody tweets anything, okay, basically it will be uploaded and it will be available online. So data production speed is quite rapid. The volume size, however, is actually quite small because the type of data that you're dealing with is essentially text data, not more than 140 characters, which means to say that the volume of the post itself is actually not very high. Though these days, you know, I think Twitter has sort of expanded to not just utilizing text, but also pictures and videos. Okay, so in some ways, you know, this particular aspect of volume perhaps, you know, is expanded to some degree. The next thing we need to talk about when it comes to data is really about the variety. How many different types or forms of data do we actually have? Okay, how is it oriented from different types of things? Okay, so in a way, you know, this variety of data adds a degree of complexity to the way we manage the data. You know, it will take up more volume, more space if, let's say, the data actually involves different things that perhaps have bearing on it. And then also, you know, it may also have some challenges when it comes to different data types, okay? Being read by different types of machines, okay? Another thing it has to do with veracity. So veracity relates to how accurate your data is and how trustworthy this data can be. So veracity is also very important, okay? Ensuring that your data is accurate, ensuring that there is no doubt in your data set. and making sure that people are willing to actually put their faith and their trust in your data. Lastly, okay, we talked a little bit about how do we determine value for data. Okay, how do we determine what is valuable data, what isn't valuable data? So these 5 different V's basically are the characteristics of what big data is supposed to look like. Okay, so we tend to think about data just simply by the volume, but actually, there are a lot of other aspects that we tend to gloss over. Okay, and it's not just about building more data centers to handle the volume. It is also about how can we, ensure that our processing is actually sufficiently fast enough to actually deal with the velocity of data that's coming. Okay, so we also need to consider other characteristics aside from these 5 aspects. Okay, on the one hand, okay, we need to think about the inconsistencies and fluctuations in the data stream. Okay, so the variability of the data. Okay, sometimes you will get missing data. Sometimes you will get extra data for certain people, perhaps. All right, so how do you regulate, or how are you able to kind of manage these types of variance, okay, in the types of data that you're getting? The next one is visualization. Okay, and this one is a bit of a skill. You need to think about what is the best way for you to represent large data sets through different types of visual tools. Okay, so visualization is something which a lot of user interface, user experience professionals spend effort in designing, because they want to be able to grab people's attention with the visualization of the data. So they spend effort in trying to make sure that things like their color scheme, things like their choice of graphs, their choice of data representation is actually going to be effective in actually meeting people's needs. Okay, so that is with regards to visualization. Okay, the next thing is volatility. So in some cases, the lifespan of the data will actually will fluctuate. Okay, so some data, okay, you realize that you don't actually have to keep it for a very long time. For example, okay, for those of you who are on Instagram, or if you are on different types of platforms, some platforms actually have an option for you to display data only for 24 hours, such as reels and those kind of various different things. Okay, so this type of data typically quite volatile. They don't stay relevant for very long. They're only meant to be viewed maybe once or maybe twice, during a day or something like that. So one thing we realized then is that these type of data, perhaps, they might be interesting, but they're not meant to be kept for long term. Okay. Lastly, okay, some data are vulnerable. Okay, and there is some degree of security that's required for certain data sets. Okay, so the security and the ethical concerns in the data usage is something that everybody is always talking about, because this has a lot of legal implications. Exactly whose data are you using, exactly why are you using it, exactly how are you using it, and how can your company or your organization be protected just in case these data actually goes onto the hands of the wrong people. Okay. Now, this comes to the next topic, which discusses about the dimensions of scalability. Okay. This is the big topic of today. Okay, talking about the different ways in which we scale our data, and this idea is basically to come to terms with the fact that at the end of the day, our data centers are not infinite. Okay, we live in a very finite world. Everything has their limits, which means to say that whenever we create data, we have to have a place to store it, and storage space eventually will run out depending on how much data that we are actually creating. So there are limitations to our ability to scale our big data sets, okay? There are limitations to our ability to scale our big data sets, okay? And right now we're going to discuss a little bit about what are these dimensions and what are the constraints, and also how do people actually get around them. Okay, so we're going to focus on 6 different dimensions of scalability. Okay, and we're going to go through that one by one. But the idea here is to tell everybody that, look, a lot of these things perhaps are outside of our control, but some of them are within our control. Okay, so let's jump into it. Our first dimension that we want to talk about is storage. Okay, now the fact of the matter is, and this happens to everybody, I believe, is that you realize that over time, if you are using your device long enough, or if let's say you you are a very heavy computer user, you start to realize that you're running out of this thing or this idea called storage. Okay, storage is typically something that is associated with your archiving. So if, say, you spend a lot of time and effort creating a lot of files, you store a lot of videos, you store all kinds of different things, you realize that your stress on your capacity is actually very high. Okay. On the one hand, it means that you probably have to change some of your habits. Okay. And the fact of the matter is that a lot of times adapting to these kind of situations is not really so much about getting in more resources or bringing in more capacity or bringing in more storage space. It's really about how can you optimize your process in order for it to be more sustainable. Okay, so some of you, okay, who A, refuse to shut down the computer, B, refuse to delete your photos, okay, or C, refuse to delete your videos and things like that, okay? Have a little think about what are you actually doing, because when you run out of space, it really means one thing: you're hoarding everything too much, okay? Straightforward, all right? Data is not meant to be hoarded. Only really important data is meant to be kept, okay? Not all data are created equal. So storage then is nowadays a bit of a challenge, okay? On the one hand, the population is growing, the amount of media and the amount of content is also growing. It means to say that these days it is very crucial that we have sufficient storage space in order for us to maintain our competitiveness. Nonetheless, we are also quite certain of the fact that storage is also not cheap. Okay, so this is one of the challenges of big data, is that how are we able to justify the cost of increasing our storage space, but at the same time maintaining it to be accessible and also reliable. Okay, so these storage solutions are out there. Okay, so for example, Amazon Web Services, they have their S3, Google has their cloud storage, Microsoft has Azure. Okay, so there are different sort of data sort of data centers or databases where they actually charge you a certain amount for you to keep your data with them. Okay, so this is one way. All right, and this is probably the most commercialized way. It is actually very well known and things like that. I'm just going to double check. Did somebody raise their hand? Actually, our group consists of 5 members from earlier. 2 of our members are already filling the names in the previous form. Due to some destination names not showing up. Haven't found names anywhere. Can you proceed with the information is already reached 5 members? Okay. Let's talk about it in the break. Okay.
Okay.
So, okay, the second thing that we also do is this thing called distributed file systems. Okay. Distributed file systems are similar to, say, blockchain data. All right. Basically, the idea is that there is a distributed ledger that actually has your files sitting on different systems around the world, all connected by the internet. And this distributed file system basically reduces the burden on a single center and actually places that burden on the multiple different centers at the same time. So these files are not necessarily stored in one place. They may be stored in multiple different places, but all of these systems are all connected. Okay, so this is one way for us to make sure that we have sufficient storage space. Okay, so you share out the storage area. Okay. The last solution is really about data compression and indexing for optimized retrieval. So data compression is very possible. It's something that we've been doing for a very long time. But traditional data compressing processes have not have evolved quite a long way, but has not really been able to circumvent the need for more and more space that is actually required by our current generation of IT companies. Okay, so people are still relying on data centers. First and foremost, they rely on cloud solutions next, okay, and then so on and so forth. Mainly because of costs, but also mainly because of security. They want to ensure that their storage solutions actually not exposed or not subject to any form of risk from external parties. Okay, so that's for storage. Now, for processing, okay, there is this limitation for computers to be able to handle complex computations across distributed systems as data volume increases. So the issue here is that you realize that one thing is to have a lot of data in the database, okay? That affects your storage space. But when you have to process a lot of data, what it affects is your memory space instead, okay? So memory is really your computer's ability to carry out multiple processes or carry out complex processes at one time. It requires memory. So the difference between storage and memory is the difference between hard drive and RAM, okay? So with that in mind, we notice is that nowadays, a lot of next generation, especially AI, machine learning, as well as natural language processing, tends to require a lot of computational power, okay? And this computational power, okay, has different bottlenecks in order for it to attack large data sets in real time, okay? What it means is that on the one hand, you need to increase your processing speed, okay, if let's say you want to actually tackle a bigger problem. But on the other hand, there are also other solutions out there. So for example, we have this idea of parallel computing frameworks where different companies have come up with their own solutions in order to actually achieve this. The second one is edge computing. So basically, it will actually run the supercomputer near to the particular source so that the data can actually be wired directly from that particular machine directly to the supercomputer in order to process the data locally, okay? Lastly, okay, we also are able to install accelerators, either GPUs or AI accelerators, in order for more intensive, more complex machine learning models to be run at the same time, okay? So when it comes to processing speed, we realize is that, there are still speed bumps and bottlenecks in order for our ability to process large data at one time, okay? Large data at one time. If you're talking about, okay, I just need to add more RAM, it's kind of true, but the thing is that when you're dealing with millions and millions and millions of data sets, perhaps, you need to think a little bit deeper about what are the different types of computing options that are out there for you to actually overcome this, okay? The third thing is analysis. So analysis talks about our ability to actually derive insight from our data sets efficiently. Okay. So with analysis, our challenge is to ensure that our tools are able to handle the increasing data without excessive computational time. Okay. Now, I can vouch for this because if let's say, for example, when I was doing my own research, my software also has limits to the degree of analysis it can run at one point. Okay. And a lot of these analysis parameters, okay, are very much determined based on your memory, but also B, your software updates, okay? So certain algorithms have very limited capacities to actually derive insight, okay? Nonetheless, this is growing quite rapidly simply because developers are using AI to help them these days, okay? So the solution for this is that perhaps, we can use machine learning or AI-driven analytics to actually help us to determine pattern recognition, for us to ultimately analyze complex networks and also be able to query these large-scale databases in order for our analysis to be a lot more clearer, makes it sure that it is easier for people to understand it, and at the same time, insightful enough for us to help make decisions using these kind of data sets. So this is actually to some degree not necessarily a physical limitation. It is more of a limitation of more of a mental limitation in that sense. Okay, we only can analyze up to the point where we are aware of these particular methodologies. All right. Anything more than that, okay, might be a challenge for all of us. So this requires the researcher to constantly learn, as well as requires the developers to find new ways in order to incorporate new research methods and also new research styles into their analysis suite. Okay. The fourth thing has to do with network. Okay, so this particular limitation relates to ability of this particular network to efficiently transmit large data volumes. Okay, this one is more of a physical limitation compared to the last one. All right, now in this one, we notice that there are latency and barrier limitations whenever you transmit real-time data because anything to do with electrical basically still has to obey the laws of physics. Okay, this means that we will get lag when we pass a lot of data from one place to a very far place. Okay, that is just the nature of data transfer. Okay, nonetheless, data synchronization is still something that people are working on across the global network and trying to make it a real thing. Now, there are solutions to this. Obviously, there is this idea of the content delivery network to ensure that data access is distributed equitably and that everybody is able to get onto the 5G network, onto the fiber optic network. Okay, so another way for us to do this is this thing called edge caching. Okay, so for those of you who are keen to get more marks, perhaps you can do some further reading on that. That actually talks about how can we reduce latency in frequently accessed data. Okay, so networks, in a sense, infrastructure is very much dependent on political will. Okay, if let's say the political will is there, then generally speaking, a lot of these things can get done. Sometimes, if say there are philanthropic players who are looking to actually do this in more on a larger scale, okay, then you probably get some degree of progress made in this particular area. Okay, the fifth one, okay, regards to the user. Now, the user relates to the ability of a system to support a growing number of users accessing data without performance degradation. So what this means is that if let's say we have X number of users, okay, it's still quite okay. Okay, a lot of people still can use it very well. But one thing you realize is that the moment you add more and more and more and more and more users, suddenly your performance might have an issue. Okay, there may be some degradation in your performance, and this usually relates to the amount of space that you buy. Okay, that's number one, and also to some degree, some of the website related subscriptions maybe needs to be upgraded. Okay, in order for it to avoid this kind of performance degradation. Whether you like it or not, a lot of these things still need to be paid for. Okay, so I don't recommend doing it while you're a student. Now, if let's say you are planning to start your own IT company, then maybe these sort of things will be very helpful for you. But if not, this could also be very interesting information for you to think about, okay, with regards to the sort of growing digital economy in the future. Okay. The last thing, so the hard part about the user is really about how do we manage concurrent access and high traffic spikes? Okay, how do you prevent your app from crashing or prevent it from lagging or freezing when a lot of people are using it at the same time? Okay, so ensuring that this data is still accessible across different types of audiences is very important, and making sure that people are able to access it when they want to access it, okay, is actually also a challenge as well. So one way to do this is this idea of load balancing and also auto scaling, okay, in the cloud, and also efficient sort of program design in order to make sure that the application or the particular platform is not storing too much data in its back end as well. And this actually helps us to actually be able to determine, okay, what are some design flaws or some design best practices that we should actually include in to make sure that our algorithms ultimately will deliver user-friendly type of features. Okay. Okay. Next slide. I think this should be the last dimension of scalability. Okay. This dimension talks about our ability of our software and our platforms to evolve and adapt to increasing data needs. Okay. So on the one hand, when we talk about the user, we're talking about the user experience or the user interface. On the other hand, we talk about the application, we're talking about the product itself. Okay, how well is it able to evolve and adapt to what other people are needing? Okay, so the challenge here is to ensure that this application is able to handle different challenges thrown at it without having to redesign the whole thing frequently. And this actually requires us to actually utilize different case studies in order to determine that, yes, this app will actually work if, let's say, we actually did this, or we did that, or we did that, or we did this. Okay. So ensuring that this application is able to handle it, okay, is a big part of making sure that these apps are actually up and running. Okay, you don't want to have to constantly redesign your app. Okay, you probably only want to be able to send in a ticket for some kind of what's the word? Some kind of improvement is only periodically necessary. Okay. Nonetheless, okay, this is only so much we can, also so far we can go. A lot of apps also still need a lot of updating every once in a while. So microservices architecture for this modular flexible applications normally are the solutions. We try to find new ways to actually use API-driven development so that it all integrates well. And then also, there are also some concepts called containerization so that these services can also dynamically scale as well. Okay. All right. Okay, we're going a little bit. It's apparently not a lot of content. All right. So let's take a break for the time being. Okay. Just a 15-minute break, and then we will come back at 2:50 for the remaining lecture. Okay. Dalila, are you there? Dalila, are you there? All right, never mind. I'll contact her later using WhatsApp. Is everybody back? Give me a thumbs up if you're here. Okay, some people are here. All right, great. So we'll keep going. This is not meant to be a very long lecture. Okay, so we will go through a few different case studies and also just a little bit about, how can we actually use big data in science communication, and what are some aspects that we see are quite important for science communication using big data. Okay, so let's go. All right. So how do we use big data in science communication? And this is something that I'll be talking about next week. All right. Let me just talk about this for a bit. This is something I'll be discussing next week. When I'm going. So I'll be in Beijing next week. Okay. I'll essentially be giving a keynote, I guess. Okay, I think it seems to be a plenary presentation. It seems like it's keynote. It's a little bit confusing because I am it's funny. So what happened is that I text people in China using I text in Chinese to people in China, but most of the time I'm using AI because I'm not that good at reading. Okay, but then I feel that when I text in Chinese, people are a lot more easier to communicate with. So judge me for all you want, okay? But this is something that I feel it kind of puts people at ease. Okay, that's the reason why I do it. So I don't read very well, but then it seems to me like they want me to give a keynote speech. A little bit last minute, but then I'm gonna do it. So just a 15-minute discussion, and the convention that I'm going to is the China Science Fiction Convention. Okay. So how did that start? Okay, so the idea was that last year when I went to Beijing, I went to Beijing last year with about 15 of students from this particular program, from the science communication program. 15 of them, they were all actually under my supervision for research projects. Okay, and they were not everybody. There were only about half of them. Okay, so about 15 students followed me to Beijing, and they had the opportunity to present their work to various experts from the China Research Institute of Science Popularization, which are the people that I work with in China. So, part of that particular research institute, there is another research center that focuses on science fiction, which is a big part of the science popularization policy in China. Um, in um, in a sense, they are trying their best to advance the science fiction genre in filmmaking in China, mainly because they see it as an integral vehicle to popularize science and technology among the society. Okay, and the reason why they want to do that is mainly because they have two major sort of successes in the box office. Okay, And that sort of sparked the interest. Now, what they have done is that they have actually built a science fiction cluster in Sogang, the industrial park in Sogang, which is on the southwest part of Beijing. Okay. So if you know where it is, it's where they do the ski jump during the Winter Olympics in Beijing. Okay, so it was actually quite interesting. Managed to see the old ski jump complex. And so basically, I'm going there for a convention next week. I'm going to be speaking, and the reason why is because two groups from under my supervision last year and one PhD student are working on the idea of science fiction as for science communication. Okay, particularly using China as a case study. So, and this semester I have another group who's working on it as well. So, in a sense, this is a topic that I am sort of diving into at the moment for my own research, and so I'll be presenting next week and also meeting people in this field and trying to see how else we can do about it. There's a lot of discussion about how we can actually do some research on sort of like Southeast Asian acceptance of Chinese science fiction, those kind of discussions. But then I'm thinking about how else can we actually add value. So the one thing I'm going to be talking about next week is about how can we actually harness different technologies in order for us to improve our storytelling or our communication. Okay. Now, the thing about technology, such as big data technology, is that there's a lot of things that it can do. Okay. All of you here are probably very well versed with how technology can be used, especially generative AI, how it can be actually be used to essentially, replace human thinking or human thought. Okay. And ultimately drive, the development of narratives or storytelling or these sort of things. The danger is that we'll ultimately be replacing a whole industry using AI. Okay. And it's a very scary thought because the thing about AI is that ultimately, even though it can learn very well, even though it can be creative, but there are limits to its ingenuity. Okay. There are limits to its ability to think creatively, and there are limits to its ability to think critically. Okay. Which means to say that our storytelling ultimately, will still depend on our ability to come up with original content. Nonetheless, okay, data can still play a role in helping us to enhance our storytelling. Okay, although it should not necessarily be the main driver. Okay, it should always be playing a support role in what we are thinking of doing in terms of building narratives. Okay, otherwise, the key thing that makes a film great, or the key thing that makes a novel or TV series or anything great, is our ability, is its ability to resonate with our human challenge or our human struggle or our human concepts of good and evil, right and wrong. Okay. So storytelling is ultimately still going to be the crux of what makes great television, makes great movies, or makes great media. But these narratives can ultimately be driven by data and ultimately be supported by a lot of these technologies that we have with us. Okay. So I think these are sort of the things I'll be talking about next week. I still need to build my slides. Okay, so but essentially, I've got 15 minutes to talk about this, and then hopefully it makes sense to a lot of people. And then yeah, hopefully that works. The second thing that we can use this for science communication is that we can actually drive content towards audiences based on their behavior and their interests. Okay, so one thing very interesting that I came across is that there are apps these days that are basically um, suggesting solutions to doom scrolling. Okay, so if you don't know what is doom scrolling is you sitting in the middle of the night, staring at your phone, one post after another post on your Instagram or on your Xiaohongshu. Okay, just reading all kinds of different content from all kinds of different people. Now, there are new apps that are basically telling you that, instead of wasting time looking at other people's feeds, why don't you spend your time learning new information? Okay, which means to say that they will push you content that is basically personalized to your interest, but at a more deeper level of learning than just, the typical gossip and the typical comedy that you will see in average social media. Okay, the problem is that they charge for it. Okay, so the idea is that, with big data, not just are you able to build better storylines or build more credible storylines, but also you're also able to push your stories to the right people or push your content to people who will most likely be interested to actually read it or actually look into it. Okay. Also, okay, big data also assists us in actually fact checking and making sure that misinformation is detected early. Okay. One major concern, okay, and actually there's a big project that's happening in Suzhou University, okay, that talks about misinformation detection, okay, particularly or fake information detection, all right, particularly in relation to health information or other sort of critical areas, okay. So this kind of misinformation detection is actually very important to actually safeguard public confidence and trust in science and technology. Okay, so our ability to be able to screen information and be able to tell people what is credible and not credible makes a lot of difference in our sort of in the new media landscape that we see today. Okay, being able to ensure that facts are checked and making sure that these facts have been vetted, okay, and are credible. This will actually make a lot of difference in ensuring that our people are being well taken care of, okay, and it will not lead to unnecessary panic or unnecessary hysteria in that sense. Okay. Lastly, okay, another application would be the fact that it actually provides real-time insight for us to do crisis communication. Okay, so nowadays, a lot of people, they don't want to just hear messages from people in uniforms or people in suits and ties. They want to be able to see the data for themselves. They want to be able to track it for themselves. Okay, for example, once upon a time, um, we would turn on the news and wait for the traffic report. Okay, I don't know if any of you guys remember doing that, but nowadays that is no longer required. Okay, what we do is we open either Google Maps, we open Waze, we gotta open a map, and we look at the traffic situation happening in real time. Okay, and that helps us make decisions. That helps us rearrange our schedule. Okay, for example, it kind of gives us a few different ideas for us to kind of play around with so that we make sure that we do the right thing. So that is the kind of concept with regards to this kind of dashboards. Now, great dashboards basically provide interactive content so that we are able to relate to these kind of situations in real time. So, for example, you know, very early on, okay, in 2011, back in the day when I just got my first iPhone, for example, um, I was living in Hong Kong, and basically they finally said, okay, look, if you want to stay safe, okay, during the summer, you download the Hong Kong Observatory app, okay. Basically, that will be where you get notifications if the typhoon is getting dangerous. Okay, so the minute you see a black flag, okay, you need to buy stuff to keep at home. You cannot go outside in case you get swept away by the wind, okay, and things like that. So so those are the kind of situations where, you know, people are starting to believe that, okay, I don't need a talking head to tell me what's happening. I want to know the nitty-gritty. Okay, I want to be able to see the numbers. I want to know what is happening. I need to know when is it happening. Okay, everybody to some degree nowadays with our level of education, with our degree of awareness, everybody to some degree are a lot more well aware of this kind of issues already, and they want to be able to make up their own minds. Okay, what kind of risks they are willing to take during a crisis. All right. So what it means is that, you know, people are turning more to these dashboards than they are to different types of content. Okay. So although, let's say, for example, people still follow Twitter account from, say, the Highway Authority or the Twitter account from the weather department or whatever, people are more interested to see it coming from official sources or from sources they believe in. Okay, exactly what is the current situation. Okay, and that kind of takes away the potential for any, like, in terms of communication, any kind of misinformation. Okay, what are some of the challenges that we have with regards to using big data for science communication? Okay, the first one, it has to do with our privacy of our data and also potential security risks. As much as we use our smart devices to actually view content, we need to also be cognizant that a lot of times people are also watching us watch the content. Okay, so we tend to be very willing to give away our approvals for data privacy and so all those kind of things. Okay, but we also need to be very, very keenly aware that, you know, there are security risks when it comes to utilizing different types of portals, different types of platforms. Okay. The other thing that we also need to be aware of is that there are algorithmic biases and potential for misinformation. So it means to say that if you start searching for certain things, okay, the algorithm will basically consider that you might actually be interested in this thing, or it might be wired in such a way that it will neglect certain things that also might be relevant to you, but for whatever reason, the algorithm has not actually included it. So algorithmic bias basically is, in a sense, um, an inherent flaw, okay, in the way we do our searches that might actually lead to our information being inaccurate or not necessarily having the best options on our plate. Okay, so that is the issue with algorithmic bias. It could mean that we're not getting the best information out there simply because our keywords and also our algorithm has been sensitized a different way. Okay, this is a particular challenge, especially of people with different types of political inclinations. So in other countries, right, because people generally will reject one form of thinking and adopt the opposite form of thinking. Okay, either you're from the right or you're from the left, either from the blue side or from the red side. So what it means is that people have a tendency to only view information from one source and not from other sources. So it kind of makes their information become more and more polarized. And when you compound that with the fact that the algorithm basically selects for the sources that you read and the sources that you look at, okay, it means that a lot of times your biases end up getting amplified. Okay, this is a concept known as the echo chamber effect. Okay, echo chamber effect. Okay, meaning to say that people become more and more extreme because they only listen to views that in a sense They only listen to views that resonate or that reinforce what they already believe in. Okay. So this is a very challenging thing. It means that people are getting less and less critical. People are getting more and more self-centered and a lot more biased. Okay. So that is a pretty big issue. Okay. And one of my colleagues in the Center for Public Awareness of Science is basically looking into this, basically trying to unpack this concept of modeling. Okay, he's basically trying to unpack this concept of modeling. He's basically asking the question, what goes into modeling? What goes into these sort of formulas that people are building? What goes into all of these things, and to what degree are our biases coloring our to what degree are biases basically ingrained in all these algorithms? And those are some of the questions that he's asking, because he wants to understand, like when we think about all of those models that keep getting presented to everybody, how much are we supposed to actually trust these models? Okay. So these are some of the questions that are sort of coming at us at the moment in science communication, in science, technology, and society. Another aspect that we need to be worried about is the degree of infrastructure limitations, particularly in developing regions. Now, a lot of us, all of us right now probably sit in Southeast Asia. Okay, Southeast Asia is still very much a developing region. Okay, probably excluding, say, Singapore. But the rest of Southeast Asia, to some degree, are at various different levels of developing or middle income status. So with that in mind, right, it means to say that, although you might think that Kuala Lumpur is a fairly advanced city, most of Malaysia, most of Southeast Asia are probably dealing with infrastructure limitations. Okay, dealing with infrastructure limitations. It means to say that a lot of times, our, on the one hand, access to the technologies might be limited. On the other hand, our algorithms have not really captured the experience of a lot of people who don't have access to this kind of information. Okay, it means to say that, like what the AI or what our current algorithms think of, or what our big data basically thinks of Malaysia right now, is very much skewed to how people behave in Kuala Lumpur, Penang, JB, and all of the major cities in Malaysia, simply because these are the people who have access, okay, to digital infrastructures that are relatively advanced, okay, as opposed to people living in the rural areas, in the regional areas, in the smaller towns. Okay, so there are limitations. Okay, there are some inequalities when it comes to this sort of thing. Okay, so those are some of the challenges that we also have with big data here. The last challenge that we have is, how are we able to balance the real-time dissemination and data accuracy? On the one hand, we want to be able to give data as quickly as possible. Okay, we want it to be real time, because especially in crisis situations, real-time dissemination means that people have more time to react. Imagine, like, if you're putting out earthquake alerts, okay? 5 minutes, 10 minutes can be the difference between somebody being able to save their family or them not being able to save their family. Okay, so being able to send out early warning is very, very crucial in ensuring that crisis is actually, you give people the best chance to actually deal with a crisis. Okay, at the same time, being able to come up with these type of real-time accurate real-time information is also very has to be balanced with the need for data accuracy. Okay, so on the one hand, we want to make sure that we are fast. On the other hand, we need to make sure that we are precise. So this is one major challenge that we have in the building of our algorithms to actually ensure that these early warning alerts are actually released on time and on the dot. Okay, so these are some of the things that we feel probably will have are still sort of works in progress, perhaps maybe not discussed enough, and also in a way helps us to um, kind of be a little bit more realistic about what we can achieve or what we can't achieve with big data opportunities in front of us. Okay, so I'm going to go through a couple of case studies and then I will wrap. Should definitely, hopefully, finish before 4. Okay. So here's a use case, right? The EOS this system over at NASA. So NASA is a national aerospace agency for the US. It's a very old agency. It's responsible for sending people to the moon and also sending people into space. Okay, they do other things as well. Okay, but basically that is what they're famous for. Now, NASA basically collects and manages an extensive amount of Earth-science data because they actually have this system in place called the Earth Observing System Data and Information System, EOS. Okay, so this system is basically a network of different satellites that provides global researchers, policymakers, and the public with access to climate-related data sets that helps drive scientific discovery and inform policy decisions. So, using satellite technology, they are able to observe, monitor, and ultimately, in a sense, predict changes in the climate, changes in Earth sciences. Okay, so this is the purpose of this particular system. So NASA is basically collecting it, and then basically managing it. All right. Now, here are some of the aspects or some of the concepts that we need to think about when we think about this particular system. Okay. First of all, you need to consider the fact that you have a lot of different data sources coming through this particular system. Okay. First of all, it is actually coordinating between multiple different satellites. Okay. All of these satellites are continuously collecting terabytes of atmospheric, oceanic, and land-based data all the time. Okay. So when it's collecting all of this data, it is collecting high volume, multiple sources of data every day, all the time. Okay. Aside from that, okay, there are also ground-based observations from different weather stations, research vessels, basically ships, and also airborne sensors that help to complement the satellite data. So in total storage, right, this is actually currently storing petabytes of climate data with rapid growth as new missions generate more information. So one thing you realize is that in this particular exercise or in this particular project, you are dealing with high volume of data, okay, and multiple sources of data, which creates a burden on our ability to keep the data and also be able to handle the data as well, okay? So the challenge with maintaining this system, okay, is that how can we ensure that we are able to contain the growth in data? How are we able to ensure that as the sensors continuously get upgraded, the resolutions of the photos get more and more detailed? Okay, we keep sending satellites up to space, we add more satellites in. It means to say that our data set keeps expanding all the time. Okay. Aside from that, okay, everybody that joins this one will have different data formats for all of the different types of data. So there are structured data, okay, there are unstructured data, semi-structured data, and there are also unstructured data. All of these need to be able to sit on the same platform in order for it to be accessible to everybody. Now, nonetheless, this is also very important because it provides researchers all over the world with real-time access to all of this data for them to do climate research and also for different agencies to prepare disaster response. So it means to say that something as important as this system, okay, has to deal with very significant big data challenges, but it is very much worth it because all of these challenges means that we actually have very high resolution data about the earth sciences that are happening in the world today. And this is actually allowing us to do proper research and also for us to respond to disaster cases. Okay. So with that in mind, okay, this is a form of science communication that, it's not quite your science museum, it's not quite your science writing, it's not quite your science fiction film, but it is a integrated real-time dashboard that people are referring to on a day-to-day basis in order to be able to understand what's happening in the world today. Okay. And it works for both researchers and also for lay people. So if people want to understand what's happening in the world, you can just switch it on and basically can see what's going on. Okay. So all of this is consolidated on the NASA Earth Data Portal, and it provides open access to all your data sets through user-friendly interfaces. So it provides interactive visualizations for both scientists and also educators, and gives us real-time data access that helps us to predict and respond to things like hurricanes, wildfires, and climate change effects. Okay, so a lot of policymakers as well use NASA climate models to assess carbon emissions and global warming trends for help to help them actually make better decisions moving forward. Okay. Similarly, okay, in the climate case, we also use a lot of real-time climate modeling in order for us to help meteorologists, researchers, and policymakers predict weather patterns and monitor extreme events. Okay, so these models actually integrate a lot of data sets from satellite data and process them using high-performance computing in order to generate accurate forecasts. So same issue. Okay, obviously there is both the satellite observations and also the ground-based sensors that we see in the EOSDIS data set. But aside from that, okay, a lot of these climate models actually also include historical climate data. So for example, I met a group of climate scientists once upon a time. What they did was that they actually were collecting old logs from ships, okay, that traveled in very ancient times. Not say ancient lah, all right, but a few hundred years ago, those kind of ships, okay, those kind of ship voyages, because a lot of these naval vessels, right, actually kept very detailed logs on wind, on the sort of like wind conditions as well as the temperature conditions and all those sort of things. It makes a lot of difference for the captain when it comes to planning sea voyages. Okay, so they do use a lot of this historical climate data from these past weather records in order to help them improve their long-term predictions. Aside from that, they also use crowdsourced data and IoT data. So in other words, they look into different types of devices that are out there, and they also engage with sort of like these citizen scientists, okay, people on the ground, people who are willing to help to actually provide weather information. They actually get them to set up certain sensors in order for us to be able to tell how the weather is doing in those kind of areas. Okay, so this kind of climate modeling exercises normally also have data volumes that exceed petabytes per year, which means to say that there are various different scalable storage and processing systems that need to be put in place in order to keep everything going. Okay. Yeah, this one was the previous slide. So what are some of the challenges, right? So on the one hand, you have a lot of data you need to actually process, millions of data points every second from satellites and ground-based sources. You need to turn those data into analysis and forecasting. Okay, that is also a challenge. And also, a lot of these climate models are actually very complex, okay? Which means to say that they require a lot of power for it to actually work, okay? Because the simulations that you need to run are actually very complicated, okay? So complexity means to say that you need a lot more effort for the computer to actually be able to run these things, but it still needs to deliver real-time analysis. So it is quite a big ask. So how do people actually get around these problems? Number one, they ensure that they have access to high performance computing. Okay, So supercomputers, all right, are basically used to run these weather models in real time. And then also they also either that or you use parallel processing. So basically they use GPUs to help them to accelerate the speeds in order for them to be able to complete these simulations. Another way is that they use cloud-based big data platforms. Okay, so they use these I won't call them supercomputers, but they will use these cloud-based servers in order to help them to actually scale their processing dynamically. Okay, so when they need it to be increased, they will pay for it. Okay, and then after that, when they can allow it to be decreased, then after that, they will scale it down. Okay, there are also using distributed frameworks like Apache Spark in order to handle large-scale data streams as well. Okay, now aside from that, okay, they also include deep learning models, these kind of AI models, in order to help them improve the accuracy by analyzing patterns and doing some degree of predictions. Okay, so using AI models is not unheard of. Okay, in this type of modeling situations, it is very commonly used, mainly because you need everything to be very rapid. Okay, so it means to say that any kind of technology that's able to make a difference in helping the system make decisions is also very much required in order to actually get it to be efficient. So, in summary, what are some of the future directions that we are seeing in big data? Okay. Now, the things that I've discussed so far, right, are very much in the what we call the classical computing paradigm. Okay. Now I'm going to try to scale it back a bit. Okay, so the world we live in right now, okay, basically uses computers that run on semiconductors. Okay, computers that run using microchips designed using different types of materials that have semiconducting quality. So the stuff in your phone, the stuff in your laptops, the stuff in your tablets, all of those are run on semiconductors. Okay. There will come a time, and this is something that is currently being developed or currently, in a sense, starting to be realized. Okay, starting to be realized. Is this idea of switching from semiconductor-based microchips, okay, which have their limitations. Number one, they are, obviously the raw materials for microchips are getting less and less available, and also because they're all being, essentially monopolized by a few different countries. Okay. And the other thing is that it actually will overcome a lot of the limitations and the dimensions of scalability that I talked about earlier. So the option that people are talking now is about quantum computing. So quantum computing does not run on semiconducting. It runs more on these considered like superconducting elements. Okay, so some quantum computers are built on light-based quantum computing. Okay, some are built on things called trapped ions and various different physics type of explanations lah. Okay, it means that they're running computing. Okay, they're running all the processes of computing using new pathways, without having to use the typical semiconductor logics and all of those various different things. One thing that we've noticed with quantum computers are they become a lot more powerful, okay? And they're able to do a lot more calculations at a much more faster rate. The typical thing that people say about quantum computing is that it can do what will take a supercomputer running on semiconductors 75 years. It can do it in 2 minutes. Okay? So that is the concept behind quantum computing. Now, quantum computing right now is essentially a very much a controlled export. Okay, some people consider it a very dangerous technology because imagine, right, this type of computers can break down all of your cybersecurity networks. Okay, it can break down your, it can decrypt a lot of your, a lot of different things. And basically, it's a huge cybersecurity threat. So what it means is that the number of companies that work in quantum computing are either very small or are typically in the defense industry. Okay, so they are behind locked doors. So quantum computing companies include, we know of a few in Germany, in Canada, as well as in China. Okay, and these companies normally are normally very much state driven. Okay, or they actually have their technologies are not easy for to actually apply. Okay, so for example, how much can I say? So for example, this Denmark is building a strong quantum computing cluster. The Americans, I'm not sure what they're up to. Germany and Australia, they have one company that's actually working on this topic. Canada, there's this company called Xanadu Quantum Technologies that's working on this as well, working very closely with the Canadian government. In China, the big quantum computing space is actually in Hefei in Anhui province. That is probably going to be the center of quantum computing, but it's actually part of a larger channel between Beijing to Shanghai. Okay, that's sort of like the quantum computing corridor for China. Nonetheless, okay, the big quantum computing company in China right now is actually based in Shenzhen. Okay, so there are a lot of things that are happening in this space, and we feel that quantum computing will basically be a good answer for the vast climate data sets that would actually be able to do the weather modeling much faster compared to the current supercomputers that we see. Okay, but a lot of things need to change for quantum computing. Even the language of programming is also not the same as classical computers. Okay. Aside from that, okay, there's also this idea that we can run edge computing on satellites. So rather than getting everything to be sent to Earth and then computed together on Earth, they are talking about how about we run the AI models directly on the satellites, which means to say that once you send it over, it's already cleaned up to some degree and is already ready for further processing. It will actually help to reduce the lag, okay, between weather predictions. Okay. Another thing that people are saying is that if we are able to power 5G networks across the countries, you are able to ultimately integrate more IoTs in order for you to produce real-time sensor data collection with hyperlocal forecasting. Okay. So, but this requires a lot of coordination on the ground to ensure that these 5G networks are fully deployed across various different countries. Not easy to do, especially for countries that are very large or for countries that have very serious geographical limitations. Okay. So, in summary, okay, big data is not small, it is quite big. However, there are limitations to big data in terms of its infrastructure as well as its performance. On the one hand, okay, big data is really all about being able to handle massive data sets. But massive data sets requires high capacity storage. It requires powerful processing. It requires fast networks. Okay, so all of these things play a role in being able to allow big data to really function well. Okay. Nonetheless, this kind of scaling also requires AI-driven analytics so that you can actually use the data that you're actually building. And these platforms are basically useful for different types of people, such as scientists, policymakers, and also the public. We also cannot lose sight of the fact that data privacy is also a big question, okay? And there are cybersecurity threats and also potential misinformation risks. So the ethical aspect cannot be ignored lah. Okay, and this is all very pertinent when it comes to how we are able to communicate open science. All right, I think that is all I have for today. I hope all of you will find it useful. Okay, can I just know if there are any questions at this point? I'm going to turn off the recording. One moment, yeah.